Recording started.
Okay, good evening everybody. I do want to welcome you to the Spring 2012 semester of Organic Chemistry. For those of you who don't know me, my name is Ayorinde. I do have my name tag right there, so take a look at it. And for those of you who are new to the class, I will advise that you also make a similar name tag so I get to know you. By the way, how many of you are new to this section, to my class, this semester? Oh, okay. Okay, hopefully during the course of the semester, I will get to know each one of you. I see Shine is right here, Sirita there, Tony. Let me see, I need to go through my name list. Jessica right here. Okay, I come back to you. Ambria, Emma, the regular people in front. Mela, Dylan, okay. Okay, anyway, you are all welcome. And of course, as you know, this session is being recorded. And everything we do in this session, of course, will be posted in your Blackboard homepage. So I do advise that you take advantage of this. Another thing I would like to tell you, the syllabus is made available to you. It's also in Blackboard. Please, I beg you, please read that syllabus because there are some information there that are very important, particularly with respect to how the grades will be assigned at the end of the semester. I do not want to see any one of you ask me, how are you going to assign the grade? What kind of grade are you going to give me? I do not give a grade. I only record the grade. So whatever you do, I record. If you want an A, I give you an A, based on what you perform in your quizzes and your examinations and online quizzes. For those of you who are new to the class, we are going to have a series of quizzes, examinations, and online quizzes. The online quizzes will be based on the our assignment, which will be assigned every week. For example, we are going to do chapter 14 today. We're also going to finish chapter 14 today. That's right. With Tony looking at me. We're going to start chapter 14 today. We're also going to finish chapter 14 today. We may have a quiz on Thursday. You don't want a quiz on Thursday? How many people don't want a quiz on Thursday? How many people want quiz on Thursday? Everybody say they want quiz on Thursday. No? Okay, so since this is a democratic system, there will be a quiz on Tuesday, next Tuesday, right? So anyway, as we are going to have a series of quizzes, examinations, and of course our online quizzes. As you know, many of these quizzes will be dropped at the end of the semester. We're also going to drop one of the 4 one-hour exams at the end of the semester. So please take a very close look at the syllabus. Everything we need to do in this class is actually specified in that syllabus, including the assignment of points for class participation. We do encourage you to ask questions in class. No question is a stupid question. So believe me, just go ahead and fire at me, and if I make mistake, let me know, because I do make mistakes once in a while. Do not be afraid to point out whatever mistake I made. That way we will have some participation from each one of you. So I do assign points for class participation, and also at the end of the semester we have surveys. I do assign points for all that too. I see Tony looking at me frowning. Why are you frowning, Tony? Tony is one of my favorite students. You see me jumping and picking on Tony, and then Shine right there, and Sirita. Okay, so anyway, so you're going to hear me calling each one of these people very often, because they are always troublemakers. So okay, anyway, so we are going to start with chapter 14. Is there any question before we get started? No, any question on the syllabus? Yes, go ahead. Do what? Yes. Okay. Okay, you will find that chapter 14 is a very, very short chapter. Indeed, many of the chemistry in this chapter we have done already. So this is just almost like a review for most of you, indeed for just about all of you here, since you've already taken organic chemistry 1. Is that Brina over there? Is that Brina? Brina Davis? No. I keep missing your name with somebody else. Okay, anyway, so we are going to start with chapter 14 now, which of course is taken from the 8th edition of McMurray. All of you have a copy of the book, and you also need the access to OWL online. Once you buy the book, of course, you are automatically given access to the OWL assignment. Okay, so now since there is no question, we are going to start our lecture right now. Chapter 14. Now, what does chapter 14 deal with? Chapter 14, essentially, what it does, we are going to be dealing with the chemistry of conjugated alkenes. My glasses. So chapter 14 deals with the chemistry of conjugated alkenes, and of course with specific or particular attention given to electrophilic addition reactions involving conjugated alkenes. And finally, we're also going to deal with Diels-Alder cycloaddition reactions, also dealing with conjugated alkenes. And before we leave this chapter, of course, we are going to be doing a lot of reaction mechanism. This chapter deals with a lot of reaction mechanism. So this is an introduction to many of the mechanisms that we are going to be dealing with during the course of the semester. Of course, like I told you before, this chapter also deals with a lot of the reactions that we've done before. Now, if you go to the next slide, on this slide, what we have listed a list of items that we call learning outcome objectives. You should use these items on this slide as a form of study guide. In other words, I will advise you to revisit this particular slide, take a look at each one of the items here, and ask yourself whether you know how to solve, or you know the particular items and how to do them, or how to answer questions that relate to these particular items. For example, upon completion of this chapter, you should be able to identify conjugated alkenes or conjugated molecules. Okay, so if I give you a molecule, you should be able to tell me this is a conjugated molecule. Okay, once we finish this chapter. You should also be able to write the mechanism of electrophilic addition reactions involving conjugated alkenes. So, as you go along, just keep coming back to this slide. Ask yourself, can you actually answer any one of these items here? Can you solve any question dealing with any one of these items here? If the answer is no, then you need to go back and revisit your notes or the webcast that we post on on the Blackboard. Or indeed, maybe you might even want to talk to me or talk to some of your friends. One advice I will give you, it's actually very good to have a study group. As having a study group is very, very important. And of course, that doesn't mean that you shouldn't come to me. For those of you who do very well, you find that it is actually very useful for you to approach your professor all the time. It's nice for me to know you, and it's nice for you to know me too. And that way, who knows, you may be asking me for a letter of recommendation down the road. If I don't know you, I couldn't write it. Okay, so therefore, my office is always open. I'm in room 120. Make it a point of duty to just stop by and let me know how you're doing. Okay? So anyway, this slide I actually use as a form of study guide. So now the next question that comes to mind is, what are conjugated alkenes? What are conjugated alkenes? As you can see with these examples on this slide, conjugated alkenes are alternating double bonds that are separated by single bonds. In other words, in this molecule here, you can see here there is a single bond here separating the two double bonds. So the conjugated alkenes, therefore, are alternating double bonds that are separated by single bonds. Okay. So in this particular example, we call this molecule here isoprene. That is the common name for this molecule, this particular molecule here. On the other hand, the IUPAC name is 2-methyl-1,3-butadiene. For those of you who did, of course, all of you who did Organic 1, we did nomenclature last semester. So you know it is butadiene. Why do we call it butadiene? Anybody has an idea? Why do we say butadiene? We have two double bonds, and what is the longest carbon chain? 4, exactly. The longest carbon chain is 4, and of course you have the double bond in position number 1 and position number 3. So that is why we call this 1,3-butadiene. And of course, the methyl group is in the 2 position, which is right here. Okay? So therefore, if anybody asks you, what is a conjugated alkene? What is a conjugated alkene? If I ask you, what is a conjugated alkene? What will be the answer? Exactly, alternating double bonds separated by single bonds. Another example is this molecule here, which is 1,3-cyclohexadiene. It is cyclohexadiene because it is a cyclic molecule which contains 6 carbon atoms. 1, 2, 3, 4, 5, 6. Contains 6 carbon atoms, so we say cyclohexa for 6. Diene because it contains 2 carbon-carbon double bonds. And of course, those 2 carbon-carbon double bonds are in position 1 and 3. Because this is 1, this is 2, of course, this is 3, and this is 4, 5, and position 6. Okay, now, we also show you another example here. This big molecule here, this is another example of a conjugated alkene. You notice what we have here. What do we have? We have alternating double bonds separated by single bonds, right? And this particular molecule here we call beta-carotene. This is the molecule that gives carrot. Most of you eat carrot, right? This is what you eat when you eat carrot. This is the molecule that gives carrot the orange color. Indeed, most food items that you eat that contain orange, this is the molecule that gives that color. Okay, so this is called beta-carotene, and of course it is a conjugated alkene system in which you have alternating double and single bond. So you can see here, just based on what we've done already, you should be able to deal with item number 1, right? So if I give you a molecule here, right now if I ask you to draw a conjugated alkene system for me, you should be able to do that based on what we've just done. Now we also do have other examples. For example, let me draw a few other examples here. Supposing I have this. Supposing I have that molecule. This is a conjugated ketone. Conjugated ketone. Okay? It is not a conjugated alkene because for alkene you must have carbon-carbon double bond. But here we have one carbon-carbon double bond separated from a carbon-oxygen double bond by a single bond. So this is still a conjugated system. Okay? So therefore, this is a conjugated ketone. So keep in mind, to have conjugation, you must have a carbon-carbon double bond, another carbon-carbon double bond, or carbon, in this case, carbon-oxygen double bond separated by a single bond. Anytime you have a triple bond separated by a single bond, it is a conjugated system. Okay? Another example of a conjugated system, you could have this. Okay. This is also another example of a conjugated system. In this case, we have a carbon-carbon triple bond conjugated with a carbon-carbon double bond. Do you see that? Okay. In other words, we have the carbon-carbon triple bond. In this case, carbon-carbon triple bond separating a carbon-carbon double bond, and that is separated by a single bond, which is right here. Okay, this is also a conjugated system. So the point is, anytime you have multiple bonds separated by a single bond, then you have a conjugated system. Now, what I want to do now, I want to give you a more global definition of conjugation. Now, if you take a look at each one of these molecules, what do they have in common? Anytime you have conjugation, you have, yes, what do they have in common? Sinead, you have what? Single bond, okay. They have single bond separating the multiple bond, right? Okay. Yeah, but also, some other thing they also have in common is each one of these is a series of carbon atoms or atoms that have p orbitals. Okay? In any kind of conjugation, I will show you why we say that in a minute. Anytime you have conjugation, you know, I told you that conjugation is essentially alternating multiple bonds separated by single bond. Now, if you really want to have a more fundamental definition of conjugation, you have to say fundamental definition of conjugation. I will say it is a continuous series of atoms that contain one or two p orbitals. Okay? So the more fundamental definition of conjugation is you must have a series of atoms that contain one or two p orbitals, a continuous series of atoms all joined together. Now let us take a look at this. Let us draw the orbital picture of this molecule here. For this, let us take this molecule here to demonstrate this definition we just given you. Supposing I want to draw the orbital picture, just taking us back to what we did in organic 1. Okay? Let us draw the orbital picture of this molecule. So the first thing I will do is to draw the skeleton showing all of the sigma bonds. So we have this carbon here attached to hydrogen by a sigma bond. When I say sigma bond, and the symbol is this. And now it is also, this carbon is also attached to another carbon by another sigma bond, and that is this carbon here. And this carbon is attached to this carbon by another sigma bond, which is that. And of course, that carbon is attached to this hydrogen by a sigma bond. And this carbon here is attached to this carbon by a sigma bond. And then, of course, this carbon here is attached to how many hydrogen atoms? 2. And each one of those 2 atoms, hydrogen atoms, are attached to the carbon by what kind of bond? Sigma bond. Okay, very good. So now we've drawn the skeleton of the molecule. Now, what we want to do now, to complete the valence, or the valence of each one of these atoms, we need to now indicate the p orbitals. Now, in this particular instance, we have 2 pi bonds on this molecule, this part of the molecule. We have 2 pi bonds here. So, okay, to have that, so that what that tells us is that we have a p orbital here. Remember the shape of the p orbital. We have that p orbital there. Let me change the color of this pen. Okay, we also have another p orbital here. Okay, this here is 1 p orbital, and this here is 1 p orbital. Okay, the red and the black, each one of these are p orbitals. Now on this carbon, okay, how many p orbitals are we going to have on this carbon? 2 p orbitals, because we have 2 pi bonds joining this carbon and this carbon. Okay, so therefore let us do the same thing here. We have p orbital here. Change my pen. Another p orbital here. Keep in mind the p orbitals have 2 lobes. Okay, one on top, one below. Those are the p orbitals. Now let us now do the same thing. Come to this carbon here. This carbon is bonded to this carbon by a sigma bond and a pi bond. Okay, we say pi bond. For pi. Okay, so this carbon is bonded to this carbon by a sigma bond and a pi bond. So to show the pi bond, we must have a p orbital on this carbon here. So let us have a p orbital here. So that carbon has a p orbital. So that means this carbon must also have a p orbital, right? Okay, so now keep in mind that each one of these orbitals has an electron. We have electron here, electron here, electron here, electron here, electron here, electron here. And to get the pi bond, you remember what we did the last semester, there is a side-to-side overlap of the p orbital in order to form the pi bond. So what do we get? We get a side-to-side overlap here between these here. Okay, so those 2 electrons now are in the pi orbital. Okay, now the same thing happens to here. There is a side-to-side overlap of this here. So now what do we have? We now have 2 pi bonds, because those orbitals are now sharing electrons. And inside the pi bond you have 2 electrons. And so that is how we get the 2 pi bonds here. Okay, so what we've simply shown you here is the orbital picture of this molecule. Okay, the same thing happens here. So here also, we have a side-to-side overlap of this p orbital and this p orbital. So now you form a pi bond, and that is why you have a double bond here. Now, so what do you now see in terms of the definition of a conjugated system? What does this tell you? Each one of these carbons here, this, and this, and this, they all contain p orbitals. And that is why we gave you this definition, that in order for you to have conjugation, there must be a series of continuous chain of atoms that contain either one or two p orbitals. Okay. Now, having said that, okay, so we have this pi bond here, and that is this. Okay, two pi bonds here, and that is this. Now, having said that, let us now go to, supposing I give you this molecule. Supposing I give you this molecule. Okay, if I ask you, I'm going to number this. This is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6. Okay, where is the conjugation here? Which atoms in this molecule are involved in the conjugation? Okay, 1, 2, 3, 4, exactly. Each one of those atoms, what do they have in common? They are p orbitals. They all are p orbitals. Now, about the carbon on atom number 5, is that involved in the conjugation? No. What is the hybridization of that carbon? sp3. So in other words, this carbon here is an sp3 carbon. So what this is telling us is sp3 atoms are never involved in conjugation. sp3 atoms are never involved in conjugation. The same thing here. This atom here, this is also an sp3 atom. It is not involved in the conjugation. So therefore, the conjugation in this molecule only involves atom 1, 2, 3, and 4. Okay? Now, what is the consequence of conjugation? When we say conjugation, what do we mean? If you go back to this, what this means is all of these electrons in these p orbitals, they could move along the chain of atoms as a result of resonance. In other words, they could move along this chain as a result of resonance. Now, what do we mean by that? Okay, supposing therefore, if I have this molecule here, if I have this molecule, okay, if I tell you to draw the resonance structure, a resonance structure for this molecule, what do we normally do? We simply move. Sorry about that. Too many bonds here. Okay, I do want to have this here and have this here and have this. Okay. So now we have conjugation. Now, if I tell you to draw resonance as a result of the fact that all of these orbitals or these atoms, they contain a chain of p orbitals, those electrons could move along the chain of atoms. For example, the resonance structure for this, I could draw a resonance for this, in which what do? when you draw resonance, all you do is move electrons, right? I could move the electron to here, okay? Keep in mind that this pi electron here is between two p orbitals. All I'm simply doing will be to take this electron from here, that is between this orbital and this orbital, move that electron to this orbital, and this orbital has nothing. And that is what we're doing. So let me go back to this. Okay, so that is exactly what I've done here. See, that arrow simply means that I am moving that electron to here. All of these two electrons that is in the pi system, I am moving them to 1p orbital. And what do you have? Now you have I move those two electrons here now. Okay? If I do that, what will be the formal charge on each one of those atoms? You draw the rest of the molecule here. What will be the formal charge on each one of those atoms? Here and here. Any formal charge? Okay. This becomes what? Plus, because I moved the electron away from it. And this becomes what? Minus. Okay? These two are resonance structures. So what have I done? All I've done is to move electron from one p orbital to another p orbital. And that's all you have to do when you draw resonance structures. Okay? Now, I could now continue to do this. I could move these two electrons now. I could move them to here to form a pi bond between this carbon and this carbon. If I do that, what do I need to do here? Move this away, because carbon must only have 4 bonds. Okay, so I move this to here. Okay, so now we're going to have a new resonance structure. And all of this is possible because we have a chain of p orbitals. And you could move electrons to those p orbitals. Okay, so now let us now draw the resonance structure that we get from here. Keep in mind, this is the symbol for resonance. Okay, so that resonance structure now will be this. Positive charge is here. Now this here. I now move the double bond is now here. Okay, since I moved this pi electron, these two electrons in the pi system to this, so now that becomes, that now has a negative charge. Of course, the metal is still here. Okay, of course, now I have this. So I could continue to write resonance structure, as many resonance structures as possible. Now, what is the consequence of this? When it comes to reaction mechanism, we're going to begin to see the consequence of the ability of this electron to move around. In other words, you will find this here, this carbocation here, will be acting as electrophilic site, right? Okay? And this could act as a nucleophilic site. So therefore, a nucleophile could come here, attack this carbon. Okay? Or if we then move this electron to here, a nucleophile could also come to attack this carbon. So depending on where you move the electron, you could now, that would be a consequence for reaction mechanism. So we're going to see some of that before we leave today. So anyway, so now we know what a conjugated system is. So what if I ask you, what is a conjugated system? What would that be? What would be the definition of a conjugated system? A series of atoms with a series of a molecule with alternating double bonds. Okay. What would be the more fundamental definition? A series of atoms that have p orbitals, 1 or 2 p orbitals. Exactly. Very good. Okay, very good. So now you guys are beginning to get the picture. So, yes, you have a question? Okay. Okay, so now we have answered the question. Yes, go ahead. Can you raise your voice a little?
When you go from a pi bond to a single bond to a single bond, and then a pi bond will get a specific pattern.
You mean when we say the alternating?
When you call it conjugated.
Mm-hmm.
When you say the conjugated, you have a double bond, and then a single bond, double bond.
Okay, I got you now. You know, okay, let me see if I get, let me go to a new page. I think I have an idea what you're asking. I believe the question, what's your name? Okay, the question Patrick is asking here is, if I have this, you know, tell me if I'm correct now. If you have this, okay, would this be a conjugated system? Is that the question? In other words, you have this double bond separated by two single bonds. Is that right? Is that what you're saying? No, it will not be, because this here is an sp3. There's an sp3 carbon atom between those, okay, and that cannot be involved in conjugation. Keep in mind that for conjugation, you must have a continuous series of atoms that contain p orbitals. In this molecule here, this carbon here does not contain p orbital. Plus, it is, you know, if you just go by the simple definition, we say alternating double bonds separated by single bonds. In this case, this double bond and this double bond are separated by two single bonds. So yeah, okay. So maybe I need to make that definition a little clearer. The double, you know, when you have two double bonds, they must be separated by only one single bond. Okay, for it to be conjugated. Is that clear? Okay, very good. Is there any other question? Now, we almost finished the chapter. After we finish this, I told you it's a very short chapter, and then we're going to do some problems. Okay. Now, the other item that we want to deal with is the Diels-Alder reaction. Remember I told you? This here, Diels-Alder reaction, cycloaddition reaction. Okay, now let us look at what does that mean. Okay, now we have begin to look at the reactions of conjugated alkene system. To do that, this look a little bit more complicated. Let me give you a very simple example. For Diels-Alder reaction, Diels-Alder cycloaddition reaction. Anytime you have a conjugated system, let us do a very simple one. We have a carbon-carbon double bond here, another carbon-carbon double bond here, and then you have a single bond, one carbon-carbon double bond like this molecule here. Let me use a different pen so we can see that better. I take this molecule here. This is your regular alkene, carbon-carbon double bond. Now, for Diels-Alder reaction, we refer to this, of course, as a diene, and we refer to this as a dienophile. Phile means something that likes something. So dienophile is a species that likes a diene. So the carbon-carbon double bond, the conjugated system, we refer to it as a diene, and this carbon-carbon double bond here by itself referred as a dienophile. That is when it comes to the nomenclature for the Diels-Alder reaction. Now, if I take those two molecules, I simply apply heat. This is the symbol for heat. I apply heat. You know what happens? This reaction will take place in such a way. I want you to follow this very, very closely. I'm going to use a different pen. This pi electron here, will move so that you form a bond between this carbon and this carbon. You see my arrow, the arrow that I am drawing here shows that we are moving 2 electrons, and those 2 electrons are used to form a bond between this carbon here and this carbon. And when that happens, this pi electron, because once you move this electron from here, guess what happens? This carbon becomes positively charged, and as such, this pi electron will move to form a new carbon-carbon double bond right here because of the p orbital that is here. So now you could then draw this, and all of these are happening at the same time. Now, when this pi electron moves, what do you think happens to this carbon? Become positively charged, and that would therefore drive this pi electron here to move to form a bond between this carbon and this carbon. And this is what we call a concerted. This is a concerted reaction. In other words, everything is happening at the same time. Bond formation and bond cleavage, everything is happening at the same time. Okay? All of the electrons are moving at the same time. And then what do you get? You get this molecule here. Use a red pen. Okay? This carbon and this carbon, this would be this carbon here. That's why I'm using a red here. Okay. Now, where the new carbon-carbon double bond, the new carbon-carbon double bond will now be here. The new carbon-carbon double bond will now be opposite to where the carbon-carbon double bond of the dienophile was. You see? Now opposite. Okay, so we started with 3 carbon-carbon double bonds. In the Diels-Alder reaction, you are going to end up with only 1 carbon-carbon double bond. And that 1 carbon-carbon double bond will be in the opposite side to where the dienophile carbons were, right here. Okay? This is what we call Diels-Alder reaction. Okay? Some people will refer to this as a 4+2 cyclo addition reaction. We say 4+2 because we have 4 electrons in the diene reacting with 2 electrons from the dienophile, and that is why we refer to this as 4+2 cycloaddition reaction, because the net process, we are going to form a 6-member ring. Keep that in mind. In the Diels-Alder reaction, the net process is the formation of a 6-member ring. Do you see that? In other words, this is what you get. Okay? Okay, that is your double bond right here. This is where the original dienophile was. Okay, now the double bond is now opposite to that. Okay. So in all Diels-Alder reaction, you are going to form a 6-member ring. Keep that in mind. Okay. Now, so that is It's as simple as that. The Diels-Alder reaction is actually a very, very simple reaction and very useful reaction indeed. Now, supposing we have this. What I've done is simply give you a very simple example of Diels-Alder reaction, but they could get a little bit more complicated. Supposing I have this. Supposing I have that, and I say, give me the product of this Diels-Alder reaction. What do you think that product will look like? Give me the product of that Diels-Alder reaction. Okay? The way you look at it, okay, let me see if I can help you out here. The way you look at it, look at this here. See this carbon here, okay, right? Think of it is joining to this carbon, right? And this carbon here, think of it is joining to this carbon. Okay, that's how it, and then of course what happens, a double bond is going to form right here. Okay? If you think of it that way, it becomes very simple. So what will be the product? What will the product look like? Cyclohexane, okay, let us draw the cyclohexane, say the color of my pen. So I will draw the cyclohexane. The double bond is here, right? Okay, now let us now draw the, where the dienophile carbons are. In a very crude way, that is the product, right? Okay, but I want you to draw it in a more fancy way. Okay, that is too crude, okay? So, in a very crude way, that is the product. This carbon here is this carbon right here with the CH2. This carbon here is this carbon right here, okay? Now, let us see if we can draw this in a more fancy way. And that is this molecule. Okay? Now, somebody's smiling. Okay, now, at this point, what you are doing, you are looking at this molecule from here. Okay? You're looking at this molecule from here. Supposing you look at this molecule from here, right? Okay, that this is what it would look like. You're looking at the molecule from the side, it will look like this. Okay, follow me. Follow me now, okay? You see? You're looking for the molecule from this. Remember, you now have two 6-member rings. In essence, you have two 6. This was the original 6-member ring. Now, this is the new 6-member ring with the dienophile carbon. You see? This is like a bridge. And that is what I've drawn here. You see it? You don't see it? Okay, okay. Not really. Okay, let me draw it in another way. Okay. But do you see this though? You see this, right? You see the carbon-carbon double bond, right? It's opposite to the carbon of the dienophile, right here. So that is the 6-member ring that will form as a result of Diels-Alder, this here. But this carbon and this carbon, this carbon here, this carbon and this carbon, they are the bridge. And that is what we have here. Those are the bridge carbon. This here is the the 6-member ring, remember we said that Diels-Alder reaction will form a 6-member ring. That is the 6-member ring that will form as a result of Diels-Alder reaction. You see that? Yes, Jessica. Oh, I'm sorry. You see, I told you I make mistakes sometimes. The double bond, of course, is here. Okay, because all I've done is to give you this molecule here. What I've done is to give you this molecule here in a different representation, in a way we could look at it from the side. Okay, right now, if you look at it from here, that is what this is. That is what this is, if you're looking at it from here. Okay? If you look at it from there, that's what the first structure is. But if you look at it from the side, okay? If you look at it from the side, then you see this bridge. Okay? Okay, so that is your Diels-Alder reaction. Yes, Emma.
I'll make a test or something. Can you just draw it halfway?
Oh yeah, of course, you could do that. You could do that. Okay. So, now let us now go to solving problems. Okay, what time do we have? Julia, you know you are lying. You know 7:30. Did you say 7:30? Oh, that was Karen. That sounds more like Karen. That sounds like what Karen would do. I know Julia won't do that. Okay, now. So it's 7 o'clock, right? So we have plenty of time. Let's now do some problems. Which one? Well, you could write it this way, if that's the way you're comfortable. Okay? if you are comfortable doing that, that's fine. But yeah, that's all the information you need to know for this chapter. But when you begin to solve the problems, it's a different story. We're now going to get into the mechanism. You see, we give you the very simple one, right? Then in the exam, we give you the very hard one. Right? Tony knows about that. I think Melody is smiling. Okay. Okay, now, let's do our problem. Okay, okay, Melody, go ahead and read this question for us.
What product would you expect to change in the reaction of 1,3-cyclohexadiene with each of the following?
Okay, okay. Very simple problem. I'm sure you've seen this before, right? What products would you expect to obtain from the reaction of 1,3-cyclohexadiene with each of the following? Okay, let us start. A. Let us do A. By the way, I took this from the back of your book. You will see problem 1421. Okay, so the first thing we need to do is we need to know the structure of 1,3-cyclohexadiene, right? I'm assuming that we all know that structure, so that would be this here. That is 1,3-cyclohexadiene. Cyclohexadiene because it's a cyclic molecule that contains how many carbon atoms? 6. Okay, very good. And you have a double bond. Okay, in position 1. Okay, this is position 1, position 2, and position 3. Of course, this is 4, this is 5, and this is 6. Okay. First thing they ask us, 1 mole. They want us to react 1 mole of bromine with this molecule in the presence of dichloromethane, this here. The dichloromethane is just a solvent, so I wouldn't worry about that. Okay? Now the reagent here is actually the bromine. Ordinarily, what happens with bromine reacting with a carbon-carbon double bond? What do you normally get? Trans addition of bromine. Exactly. Very good. Now, if that was last semester, that would be the case. But now we are dealing with a conjugated system. Right? Now, that could happen. You know, the trans addition could happen, but most of what could happen is something else. Okay? So in this case, let us look at the mechanism. Okay, let me go to a new page. This is what we want to deal with. Let us give you the mechanism of that reaction. We need to give you the mechanism in order for you to understand how we get the product. Okay, so we have bromine attached to bromine. What happens? The pi electron here will attack the bromine atom, forcing the bromine bond to break. Now, if this was a single bond, I mean a double bond without conjugation, you were going to form a bromonium ion. But in this case, we do not form a bromonium ion. See what is going to happen here? This bromine will come to this carbon. This bromine will be attached to this carbon, and because it is going to be attached to this carbon becomes positively charged, which is now become an allylic carbon. An allylic carbocation is very stable. Okay, so you're going to now get the bromine goes here. Okay, this other double bond is still here, and a carbocation is on this carbon. Like I told you, the reason why we normally do not get the bromonium ion, because ordinarily you will get a bromonium ion in which this bromine simply attacks this carbon here to form a three-member ring. Okay, for those of you who may have forgotten what that is, you will normally expect to get this. Bromine is here. Okay. This three-member ring here is what we call the bromonium ion. Bromonium. Okay. But in this case, we do not get that, because it is possible for us to get an allylic carbocation. Allylic carbocation, which is stable. Okay? In so doing, we also, keep in mind, we're also losing a bromide. This bromide here is here. Okay? So two things could happen. This bromide could decide to attack this carbon here. Okay? If it does that, if that bromide attacks that carbon, it does that, of course. Let me draw my long arrow. We get this product. With double bond. Yeah, no, I'm going to do that next. Okay. What I want to do here is just to give you the possibilities. Okay. So you could get this. Indeed, you will get this, because this bromide now has as a nucleophile to attack this electrophilic carbon. It is also possible you could draw resonance. What's your name? Okay, Kia just told us that it is possible to draw the resonance for this, in which this double bond now moves to here. Okay, if it does that, okay, let me take this out here. The other possibility is for the double bond to move here. Keep in mind, because of conjugation, and when you do that, you're now going to draw another resonance contribution to that molecule. And what do we have? We have the bromine is here, the double bond is here. What happened to this carbon? Positively charged, exactly. And keep in mind, this bromide is still here. So what do you think will happen? That bromide will now come in. Let me draw my long arrow. Call it the longest arrow in the history of organic chemistry. Okay? I typed that, right? And then what do you get? You get the other product. So now you get this product. And this product, and this bromine here. So now what type of product we have? We now have two sets of products. This is one product, and this is the other product. So the way that this question could also be asked of you, yeah, David, go ahead. Oh, yeah, oh. Thank you, yes. Double bond is still here. I wanted to see whether you guys are still sleeping or not. That's why I left it out. I did that on purpose, right, David? Okay, thank you. Yeah, the double bond is still there. Now, so now we have two products. We have this product here and this product. So the question that we ask you, if you go back to the question, give the product of the reaction of, that's the question they ask you. Give the product of this. And the product will be this and this. Now, but we could ask you the same question in a different way. I could give you this product here and say, give me the mechanism of that reaction. How did it happen? Okay? I could simply give you this product here. I don't have to give you this. I say, give me the mechanism of that reaction. Okay? Okay, so there are two different ways in which you could ask you that question. Give the product or give the mechanism. You follow that? Okay? Yes. In this case, I wouldn't even worry about that. You know, in order for you cannot tell whether this is a major or minor at this point, because there is possibility that both of them will be formed. Generally, when we ask you to give the mechanism, the major and minor really doesn't really matter. The question Tony was asking, which one of these products will be the major product or the minor product? At this point, we do not have enough information to answer that question. Yes. Emma.
If, like, the bromine attached to the other carbon of the first double bond, the products will be the same. If the bromine went to that one.
Right here.
Yeah. Like,
yeah.
Like, no, see how that one attacked and the bromine went to the right one?
It
went there, yeah.
Oh, you went, okay, yeah.
Would it be the same?
That's a good question. The reason why the bromine will not go there, because it will not form the more stable carbocation. Keep in mind that anytime you are going to form, excellent question, anytime you are going to form a carbocation in any reaction, the more stable carbocation will be formed. And that is why the bromine comes here. You see? Because if it comes here, the carbocation will be here. It will not be stabilized by this double bond. Because this double bond here, the allelic carbocation, that's what makes it stable. And it is stable because it could draw resonance, just as we've done here, to move it around. Okay? Very good. Okay, now, let us go back to the other problem. So we solved that. So let us now do B. I think everybody should be able to do B. The question here is, give the product of the reaction of the same starting material Now let us now do B. Let's take this out, this out, this out, this out, this out, this out. With ozonolysis followed by zinc. That should be familiar to all of you. Okay, so they say step 1, ozone, and step 2, zinc. Okay, what product do you think we're going to get? Cleavage. Exactly. Karen just giving us the answer, cleavage. Now, when you get cleavage, what are you going to cleave? The carbon-carbon double bond? Okay, very good. So, we all know that this reagent here, ozonolysis followed by zinc, what it does is to cleave the carbon-carbon double bond so that it does what? It gives you what? So you will cleave this carbon-carbon double bond. You will also cleave this, right? Okay. Each carbon of the carbon-carbon double bond that is attached to an hydrogen, that carbon becomes the carbon of an aldehyde. Keep that in mind. Okay, so keep in mind that you do have hydrogen here, even though we don't show it. There's hydrogen here, there's hydrogen here, hydrogen here, and hydrogen here. Okay? So, in this case, each one of these carbons that is attached to an hydrogen, keep in mind the carbon of the carbon-carbon double bond becomes the carbon of an aldehyde. In other words, this becomes a carbon-oxygen double bond. This carbon becomes carbon-oxygen double bond. This carbon becomes carbon-oxygen double bond. The same thing here. This carbon becomes carbon-oxygen double bond, and this carbon becomes carbon-oxygen double bond. So let us cleave it. So let us do the cleavage now. We now do it in a way that you can see it. So that becomes carbon-oxygen double bond, carbon-oxygen double bond. Hydrogen is still here. Okay, and that is this part of the molecule. You see that. Okay, what is the other product? Because what happens, the carbon-carbon double bond will be replaced by oxygen. Okay, so what happened on the other side? So now we have oxygen, oxygen, and of course you have this here, this here. You see that? You see that? Okay, in other words, this here, this carbon here, is this carbon. This carbon here is this carbon. You see that? Everybody see that? Okay. And on the other side, this carbon here is this carbon, okay, and this carbon here is this carbon, okay. So keep in mind, ozonolysis, what does ozonolysis do? It simply cleaves the carbon-carbon double bond so that it replaces the carbon-carbon double bond on both sides with a carbon-oxygen double bond, okay. Now, supposing this is what I gave you. Supposing I gave you this. Let's see. We have this, right? Supposing that's what I gave you. And I gave you the same reagent. Ozonolysis, step 1, followed by zinc. What will be the product? Exactly. Okay. So it will be the same product, except that we replace the methyl group, the hydrogen with methyl group, right? Is that what you're saying? Okay, good. So now we have hydrogen is here. Now this would now be this here, and this here will be a methyl group. Okay, is that what you're saying? Okay, very good. So on the other side, I'm sorry, I got too many things wrong here. Let me take this. Yeah, that's right. That is. Oh no, that's not right. That's not right. that is not right. I'm sorry about that. Okay, that is clear here. Okay, so that would be this. This will still be here, right? That will still be there. And the other side would be when we have this here. Okay, we now have. Okay, so now that is that, and then we have the methyl is here. Okay, is that correct? Okay. So depending on, because when you're dealing with ozonolysis, in this case, since this carbon does not have hydrogen, it becomes the carbonyl of a ketone. This becomes the carbonyl of a ketone. Okay? Okay, so let us now do the next problem. So, okay, so we've done A, we've done B, let us do C. Okay, what would be the answer to C? Okay, so now we're going to do C. Okay, now they want us to react the same molecule with 1 mole of hydrogen chloride. Hydrogen chloride. So what will be the product? Okay, the mechanism is similar to what we got for the when we added bromine. Keep in mind now what is going to happen. This pi electron will come in here, attach this here, the proton, breaking the hydrogen chlorine bond. Okay, and then what do you get? You get this hydrogen will be added to this here, similar to what the bromine did. Okay, so now we see how the double bond here. That hydrogen is here. Keep in mind that we did have hydrogen here initially, so this hydrogen is still there. Okay, so now you have 2 hydrogen here because the original hydrogen was there, and the carbocation is here, right? And then what do you think happens? Because we have the chloride is here somewhere, the chloride will attack, just like the bromide did. It will attack this, right? Okay. So now you form this product. Of course we have, sorry, let me do that better. Chlorine here. Of course, don't forget that there's also hydrogen here initially, so that will also be here. And of course, the double bond is still here. And that will be the product. Now, we could also make a case that we could move the pi electron to here and form a carbocation here, and then the chloride will attack, it will give the same product. Okay, in this case, it will give the same product. You follow that, right? Okay. Now, let us now see, in the case of deuterium, DCl, deuterium is the isotope of hydrogen. Let's do D to see, now begin to see a difference, yes.
Does the resonance form?
Yeah, it could, but you're going to form the same product anyway. So if you move, you see what, okay, if you do the resonance, right, we could do that. The question is, if we move these two here, let's take this out. We could move these two here. Okay, and then what do you get? You will get and the double bond is here, and the, okay, at this time the chloride of course will come in and attack this here. If it does that, just like the bromide did, if it does that, what do you get? You get the same product as this. Which is the same product as this here. You see that? Same product as this. Okay. Now, supposing you now change instead of hydrogen chloride, you use deuterium chloride, which is question number D. They want us to use the deuterium chloride. Okay. Now that would be similar to what the bromine did. Okay, so now you have this. Deuterium chloride. So what do you think the first thing that will happen? What will be the first thing that happens? Okay, the pi electron attacks the deuterium, right? Okay. And where would the deuterium go? Would the deuterium go to this carbon or to this carbon? The first carbon, because it's going to form a more stable carbocation, which is the allylic carbocation. Excellent. Okay, so now you have so now deuterium comes here. Okay, keep in mind there is an hydrogen here, but just for simplicity, well, so I don't confuse you, that hydrogen is still here. This is still here. All of these C contain hydrogen. Okay, so the deuterium goes here, the double bond is still here, and now the carbocation is where? On this carbon, right? Okay. So now, of course, we also form, when we do this, we also release this chloride, right? And that means we have, the chloride is here somewhere. The chloride now could act as a nucleophile to attack a positive center. So, two things could happen. Okay, the chloride could attack here, right? If it does that, then you form this product. So the chloride could come here, and the deuterium is here, and now the double bond is still here. So we could do that. And what else could happen? The resonance, okay? Okay, as a result of resonance contribution. So now let me take this arrow off. The next thing that could happen, you could now draw a resonance contribution as a result of conjugation, in which you now move this pi electron to here. So now you have that double bond is now here, the charge is here now, and of course the deuterium is here. And now what do you think will happen now? Exactly, the chloride will now come in with a long attack. Okay? So just as in the case of the bromination, when we reacted bromine with it, it's very similar reaction. Is it almost time? I see everybody trying to move. It's time? Okay, okay. Okay, just let me just complete this. So I owe you guys 1 minute, right? Okay, so now what product you get? You now get 2 products. These are the 2 products. This here, very similar to in the case of bromination, and this here. Okay, and so finally, I know you guys should be able to do the last one. I will leave that to you. E and F. You should be able to do E and F. So I will see you guys on Thursday, and of course we are going to finish off more problems on chapter 14. All we're going to do on Thursday, problems on chapter 14 from the back of your book, and then on next Tuesday we're going to start chapter 15. Okay, so I will see you guys around, and enjoy the rest of your day.